Okay, so I'm going to carry on talking about pi zero and in particular about path connected spaces. So that's this definition. X is path connected if the set pi zero x that we were discussing last time, the equivalence classes, the set of path components, if this has size 1. And if you think about it for a minute, what this means is that x firstly is non-empty. X has got to be non-empty because if x was empty, then the pi zero x would be empty and have size 0 instead of having size 1. And then, then for every pair of points, they have to have the same path component. So in other words, there has to be a path between. So how could this happen? One kind of special case that we can sometimes consider is like this. Suppose x is a subset of r to the n. It's a fairly common sort of thing. So now if I've got a pair of points, so I'm going to define a map, pointy bracket AB, from the unit interval to Rn by pointy bracket AB t is going to be 1 minus t times A plus t times B. Let's notice this expression is only making sense because x is a subset of Rn, it's points of x are vectors, so we can take the vector A, multiply by the scalar 1 minus t, take the vector B, multiply by scalar t, and add them together. And so, of course, at t is 0 we get A, and t is 1 we get B. But a kind of key issue about this is that I said this is a map to Rn. It might or might not be a map to X. Okay. So if ABT lies in X for all t, must be checked. Whenever trying to use this construction, you definitely must write explicitly a check that the pointy bracket ABT does actually lie in X. So in this case, but then we can regard this pointy AB as being a path in X from A to B, and that proves that A is connected to B. So, X could be like this, and then we could have some points here, point A here, point B here, point C here, and point D here. Okay, so the situation with these ones will firstly, if we just go from A to B, then so this lies in X. Okay, here we're looking just looking at this straight line path. Now we do have a path from A to C. So A is related to C, but not by a straight line path. And we could try and do the straight line path from A to C, right? But then if we go outside the space X, and A just isn't related to D at all. There's no path, straight line or not, from A to D. Okay. Yeah. So sometimes we can use straight line paths, sometimes we can't. The very simplest case is as follows. X is convex. So this is only making sense if X is kind of contained in Rn or something like that. And for every pair of points, the straight line path between them lies within the space. Okay, so do a space like this. This is convex. Whereas space like this one Y, say this one's not convex. And yeah, we'll take part of the definition of convex is that again it should not be empty. So then so convex spaces are rather obviously path connected, because if you want to path connected means non-empty and any 2 points can be joined by a path, and in a convex space you could just use the straight line path. Okay, so because this space here, this Y here is actually connected. You can go from any point in Y to any other point in Y, so it is path connected but not convex. But this one is convex, and any convex space is going to be path connected. So we'll just have one more kind of one more slightly less trivial example of a path connected space is the sphere Sn. Okay, so here notice I say n is strictly bigger than 0. And why is that? Well, what's S0? If you remember, S0 is the unit sphere in R to the 1, which consists of the two, so it's the unit vectors in the real line, in other words, plus or minus 1. That's just 2 separate points, and so that's not path connected. You can't get from 1 to minus 1 within the space S0. But for n bigger than 0, then it is going to be path connected. So let's have a proof of that. Okay, so we need to prove that any 2 points can be connected by a path, but it turns out we have to deal with one kind of special case for this. Special case is where our point B is just equal to minus A. So we're going to do the general case first, and then see what to do about the special case. Okay. So I'm going to define U is pointy bracket AB. So this is a path, not a path in Sn, it's a path in R to the n plus 1. Okay, because typically, here's our A here and our B here, and our pointy bracket AB is this path that kind of cuts across within our R to the n plus 1 from A to B, but it doesn't lie on the unit sphere. Okay, but so this it doesn't stay on the unit sphere, but it doesn't actually pass through zero. Right? If you imagine, here's 0 in the middle. The only kind of way a kind of straight line between 2 points on the sphere goes through the origin is if it's trying to go down to minus A here. Okay, so if we try to do the path from A to minus A, then that would pass through the origin, but that's the only one. Okay? If B is different from minus A, then we're not going to hit the origin. So we're not quite proved that little algebraic exercise to check that's true. But because we've not got zero vectors, that means we can just normalize. We can just divide by the norm to get vectors on the sphere itself. So let's just write that in a second. Okay, so we can take u of t and we divide it by the norm of ut. And that's okay to divide by that. Ut is not the zero vector, norm of ut is strictly positive, so dividing by that is harmless. And so yeah, we've normalized. This is now a unit vector. So we've got so that proves that we've got a path from A to B, except in the case where B is minus A. So yeah, all we have to do in the special case is just choose some third point. Okay, so here we could choose our point C here. Okay, and then once you've chosen the point C there, then if you want to get from A to minus A, well, you just go via C in 2 steps. Okay. Okay, so this is the kind of point where things would go wrong if n was 0. If n was 0, then the only 2 points are A and minus A, and you can't choose the third one. But as soon as n is bigger than 0, Sn's some infinite space, and you can choose a third point. Yeah. Yeah. Okay, so in this case, A is going to be related to C just by the general case, because C is not equal to minus A, and then C is not equal to A. So again, we can just go by, you do a straight line path and normalize it as we did before to get a path in the unit sphere from C to minus A. So this proves so this proves that spheres, positive dimensional spheres, are all path connected as we claimed.